cosine functions have different frequencies. And so we'll be able to break the function down into its many frequency components. So, if you recall, we had this approximating scheme. We had a constant term that just moves the graph up or down, followed by a collection of terms that are sines and cosines of different frequencies, different periods. So they have the basic form AK cos kx and BK sine kx. And so do you remember, what is it that determines the period or the frequency of the cosine or sine function? It's the k, exactly. And as k increases, the period decreases, which means that the frequency increases with k. All right, so what we want to do is be able to identify for a given function the coefficients a and b. And so we talked about that, and then we kind of quit talking about that, and we talked about something else completely, which was a bunch of trigonometric integrals. We did a bunch of trig integrals, and what we're going to see is that those trig integrals are the key to finding the a's and the b's. So, let's see here. I think that we're ready to jump right in. The way we are going to find the a's and b's and b's is simply to integrate this equation here. That is, integrate both sides of the equation. And it doesn't look like that's very promising, but the cosine and sine functions have a very special property that we're going to exploit as these integrals develop. So the very first thing we're going to do is just exactly what it says there. We're going to integrate. And can you guess over what set of values we integrate? X values ranging from, exactly, negative pi to pi, because remember, these are periodic functions that we're trying to represent. And that's one period of the function. And if you know what's going on between negative pi and pi, you just replicate it over and over and over. So, on the left side, we'll integrate negative pi to pi fx. Well, not knowing what f of x is at the moment, we can't do that. All we can do is just leave it. But when we integrate the right side, something interesting happens. I bet we can do that integral. A0 is just a constant, so that's the easy integration. Then we also have to integrate. This looks kind of ugly, but it'll turn out to be not so bad. We're going to integrate that sum, k equals 1 through n, of ak cos kx plus bk sine kx. Wow, that looks awful, doesn't it? Well, let's see here. Let's do the easy part first. Can you do that integral in your head? A0 over 2 is a constant, so when you find the antiderivative, it's A0 over 2 times x. Plug in pi, plug in negative pi, and subtract. Not 0, 2 pi.
So A0, 2 pi.
Exactly. It's A0 times 2 pi over 2. It's pi times A0. Okay, hey, that wasn't so bad. Now, oh, this is ugly. Well, you must know that integration can be split over the terms of a sum. That is, if you have the integral of f of x plus g of x, you can integrate each of those separately. And so this summation and this integration can be swapped. So let's do that. K equals 1, and now I have the integral minus pi ak cos kx. Well, I can take the ak out of there. So now I'm just integrating cos kx. And I've got the bk that I can take out of the other integral. So it's going to be a bk integral of sine kx. And then this whole thing is part of the sum. That looks just awful. That looks really complicated, but maybe you could tell me the answer without working too hard. Do you remember some of the recipes that we developed yesterday?
The second chunk. And the sine function.
I think we have. Did you list some integrals that we did yesterday?
The cosine.
Yes, it will. And the sine? No. It's 0 also. Both of these are 0. Yeah, this is an odd function, so it's 0 by virtue of the fact that it's an odd function. This one, well, it's not an odd function, but we did the integration and we found that, yep, it's 0. So this whole symbol soup here just goes away. And so we end up with a0 times pi, and now we have a simple way to find a0, a recipe for a0. If you divide both sides by pi, you get 1 over pi times this integral minus pi to pi of f of x is a0. So, our request for finding the coefficients that represent this wave form, this function, well, we've got one down and capital N of them to go. But we can get the others in a very similar fashion, and we'll find that similar things happen because of those impulses that we worked out yesterday. Okay, so we've got one recipe. The next of these recipes, we're going to take that same f of x equals a naught over 2 plus the sum, and we are going to multiply it by, first of all, cosine x. In fact, I should say multiply by cosine of nx. And integrate that. So on the left side of the equation, we will have the integral minus pi to pi f of x cosine nx. And now the right side, little by little. First term is that a naught over 2 gets multiplied by cosine nx. So we have a naught over 2, which can come out of the integral, cosine nx. And then all those other terms in the summation, let's see here. We'll have, we're going to multiply each of those terms by cosine of nx. So what do we get? We will get, let's see, we'll get an integral. I should squeeze that in. And the sum, what's the first term? AK. What goes with it now? Multiplying through by cosine of nx. Picture what must go with it then? Cos kx. There's also, say it again? Cosine nx. Okay? And then there's the bk terms. What do they look like? They start off looking like sine kx. But we're multiplying through by cosine nx. And that's what we are stuck with integrating. Wow, this looks like a mess again. The last one sure got easy. Well, one by one, little by little. Let's see if we can do the integrations. What happens here? Integrate cosine nx minus pi to pi, you get 0. Yeah, that's right. So this one here is 0. How about this one right here? Sine kx cosine nx. That one is 0. And what about these terms right here? Remember something happened? Okay? There are many terms here. There's the k equals 1, the k equals 2, and so on and so on. So one of those is pi. Which is that? How does that come out? When we integrated this, we did it in two separate cases. Okay, when k is not equal to n, this thing goes away, it's 0. When k is equal to n, you get pi. And so when you add up all of these terms, they're all zeros here, they're all zeros here, except one of them. So what term is left as a result of this whole integration? Everything comes out 0 except one term, and it comes out, you said it comes out pi. All right, so what we get here is pi, and what's the coefficient that goes with it? Which of those terms came out pi? It's when k equals
N.
n, okay? So ak becomes an, and so now all of this stuff disappears except for this right here. That's the only thing left in the integration. K equals n term produces an integral of pi. All the other terms produce integrals equal to 0. That's all that's left. And so now we got a recipe for a sub n. A sub n is found by just simply dividing both sides of this equation by pi. We find 1 over pi, integral negative pi to pi of f of x cosine nx dx is equal to an. So there's our next recipe. We have a recipe for all the a's now. We have two recipes, one for a0 and one for all the rest of the a's. Well, we can do this one more time to find the rest of the coefficients. So we multiply this time. You can probably guess. By sine nx. And we integrate. Okay, so our original equation had f of x on the left side. We now multiply it by sine nx. We integrate that over one period. And we do the same thing on the right. We got this a naught over 2. We multiply it by sine nx. We integrate from minus pi to pi. Then let's see, what do the rest of these terms look like? We have this sum. They started off, they were ak cos kx. What should that term look like now? ak cos kx, we tack on sine of nx. And there were also the bk terms, bk sine kx. And we've just multiplied through by sine nx, so that appears here. And all of that we we should integrate from minus pi to pi. And again, this just looks like a horrible mess. But little by little, we can unravel it. Can you tell me the result of this integral? Sine of nx, it's 0. It's just gone. So that one goes away. And how about all of these terms here? Cos kx sine nx terms, they're all zeros. What's left? Almost all of these guys are gone. But there's one left, which is when k equals n. Okay? So when k is not equal to n, these terms disappear. Their integrals are all 0. When k is equal to n, this integral produces pi. And so all that's left is bn times pi. Everything else just goes away. So once again, we divide through by pi, and we have now a set of recipes for piece of n. So we get 1 over pi, integral minus pi, pi of f of x sine nx is equal to bn. There's our recipe for the b's. So we have recipes for all the a's and all the b's now. We can find the representation of any periodic function in terms of sines and cosines. And remember, the real trick here, the real key is that these sines and cosines have different frequencies. And so the a's and the b's identify the frequency components of any function. They allow us to pick out certain frequencies or exclude certain frequencies. We can do whatever we want once we know the frequency components. Let's see, all of this amounts to this is called the Fourier approximation of a function. Fourier was a mathematician who lived somewhat before the digital era. This is something that always amazes me. Here's a guy whose life's work was done in the late 1700s, early 1800s. He had absolutely no hint, not a dream of the digital age, and the work that he did back then is exactly the tool that's necessary in the digital age. So, any questions at this point? You are a less lively group than yesterday. Yes?
If the period of the function isn't from negative pi to pi, is that why we're integrating that?
That's why we're integrating it.
So
One
if it's
period.
not, then how do things start canceling out?
What you have to do is, you can do it on any period centered at 0. So a standard way to do it is the standard notation is from negative L to L. And then, let's see here, you have,
The trig is canceling out with pi, but that not
say this is negative L, this is L. You must know the technique of integration by substitution. U substitution, does that sound right? Okay, so you do something like U equals X over L, and maybe it's, let's see here, it must be pi X over L. And that substitution simply transforms the interval from negative L to L to an interval negative pi to pi, and then all the theory that we're developing here works. So you'll sometimes, instead of seeing the B's and A's with this formula here, sometimes you'll see it integrated from minus L to L, and then there's some little minor change that's based on this change of variables. Works on any period. Any other question? You had a question too?
Oh, it was the same thing as what she said.
Isn't that amazing? Yeah.
This is more like mathematics, more historical. What's Fourier trying to work out for? Is this something you noticed or things?
Fourier was more of a physicist than a mathematician, and his work had to do with heat transfer. It had to do with when you heat a body, how does the heat dissipate? How is the heat conducted? And what's that? Thermodynamics is exactly right. And exactly how this fits into thermodynamics, I haven't the slightest idea. I've never studied thermodynamics. Okay? So, many of these mathematicians and scientists at that time were just extremely diversified. They knew many different subjects. But I think this had to do with heat transfer originally. Okay, so now what we have to do is see how this stuff works. Take a specific function and we'll calculate Fourier coefficients, and then we'll see a little demo from a website that shows how you can manipulate a sound, basically, by manipulating its Fourier coefficients. So here's our example. We're going to look at f of x is -1 on the interval minus pi to 0. And it's 1 on the interval 0 to pi. You've probably seen functions written like this, piecewise functions they're called. Does this look vaguely familiar? Okay, so can you picture what this function looks like? Between -pi and 0, the functional value is -1. So it's just a constant function down here. Here this must be -pi, and this must be -1. Then, when x equals 0, it jumps up, takes on the value 1. So now, at pi, the functional value is 1. But this is one period of a periodic function. So this thing just simply repeats itself. From pi to 2 pi, it looks like this. And from 2 pi to 3 pi, it looks like that. This is known as a square wave. It's described as a square wave. So our job is to try to approximate this square wave by sines and cosines. Well, in a certain sense, it looks just very, very crudely, roughly like a sine function, doesn't it? The sine function comes down like this, oops, and it goes up through the origin and then up to here, down again. So in some really rough sense, it looks like a sine function. What we have to do is build this out of many different sine functions and perhaps cosine functions so that they begin to look more and more like the square wave the more terms we add in. So, off we go. We're going to find A0. A0 has a recipe. The recipe is 1 over pi, integral minus pi to pi of f of x dx. Can you do it in your head? There's the function f. It is 0, and why do you think so?
So one period there.
Yep, also known as an odd function, right? Yeah, this is the odd function right here. From -pi to 0, its value is here, and then f of -x is negative f of x. It's an odd function. Your description was exactly right, but that's why odd functions have to equal 0. Okay, how about the rest of the a's? Let's look at a, well, let's see, some of the notation I've used before says a k, sometimes it says a n. It doesn't matter. You can index it with anything you want. You can call it a k or a n, whatever. So I'll stick with a k, and here's the recipe. 1 over pi, integral minus pi to pi. What is it we integrate when we're looking for the a's? F of x, but we pair it with, say it again? Cosine. F of x cosine kx. Okay. So we know what f of x is. It's -1 or 1. Oh, but wait. What's the story here? It's 0 because it's an odd function. The f of x is an odd function. You can see it here. And cosine, remember cosine? Cosine is an even function. When you multiply an odd function by an even function, it's one of those two. It's odd.
Even or odd, tell me.
When you multiply by an odd function with an even function, the result is an odd function. And so this integral is 0 again because it's an odd function. Okay, so we got all the a's equal to 0. And in a sense, maybe you can see why that's true. This thing looks a lot more like a sine function than a cosine function. Sine functions have this property where they dip down to -1, cross through the origin, and then hit +1. Cosine functions are sort of shifted off of that. And so we would expect this to look more sine-like than cosine-like. And that's what we are finding so far. So we have one more integration to do, the BKs. The BKs are going to cost us a little bit more work. We hope they're not 0 because then our whole function is 0. We don't want that. So the BKs, once again, by recipe, 1 over pi, integral -pi to pi. And this time we're going to take f of x sine kx. Here we're going to have to be a little bit clever, and then we're going to just have to work. Okay, let's look at the even-odd thing. What do you find? It's even, because this guy's odd, the sine function is odd. Odd with an odd makes an even function. What do you know about even functions? You can replace the integral minus pi to pi by 0 to pi, and then double the result. So we get 2 over pi, integral 0 to pi. But wait, on the interval from 0 to pi, what's the value of f of x? It's 1. How convenient. So now we're stuck with simply integrating sine kx dx, and we can do that.
Wait a minute, this might be a stupid question, but I thought if you have a product, you can't just integrate one part and integrate the other part, right?
You can break the interval. So
Right, the 0 to pi I'm good with, but the f of x separately finding its area and the sine of x separately?
no, we're not integrating it. F of x is equal to.
It just is 1, it's just for that part. Okay, yeah, that's true. Okay.
And
okay.
so on the interval, this is minus pi.
We're just simply replacing, but the integral is
Exactly.
still there. I'm good now.
We're
Okay.
simply replacing f
Yep, I see it now.
by what f is. We haven't done any integration.
Got it.
But we've simplified the integration, so now we can probably do it. Let's see, sine kx, can you do the antiderivative there? It's cosine. Now there's certainly a cosine. In fact, maybe it's more like 1 over k and negative. So there's a 1 over k and a negative cos kx. I think we've got all the pieces there, don't we? We evaluate on the interval 0 to pi. So what happens here? at pi, we end up with a negative cos k pi. Let's see if we can tidy this up just a little bit. We just combine all of this stuff here. So we get a minus 2 over k pi. And then we get a cos k pi. And what happens at the lower end? I've already taken care of the minus sign, so this is all we're doing. At the lower end, cosine is cosine is 0. It's 1. Yeah. So we subtract off of 1.
Fiona, did you have a question?
Yeah, for the, I don't know what it's called, I know like the, I don't know what's the integral, but like just the straight slash for the 0 to pi.
Yeah.
Is it proper to put it in the back, or does it matter if you use it like the swirly looking one?
Wow. This is very standard notation for definite integral. Do you use this notation?
Yeah.
Okay. This is when you have done the antiderivative, you have to evaluate it at the upper bound and at the lower bound. This is a very standard notation for evaluate at upper bound, evaluate at lower bound, and subtract. So that's.
So you can't do how you do it where you like put it in between the constant and then like this.
Oh, like we've done brackets around the whole thing before and put that in. You know, like if you wanted to just keep the 2 over pi out front and make it kind of brackets instead.
So you could put square brackets here, and then put the 0 and pi on the square brackets. Yeah, that's fairly standard. I'm not sure. This is an extremely standard notation. It's a.
No more integral symbol though, because we've already taken
We've done the antiderivative.
so we don't need that anymore.
Yeah, so the integral symbol goes away because we've done the antiderivative. But now we need to denote in some way that we're evaluating the antiderivative of these two bounds. That's the standard of notation right there. Well, let's see here. Yeah, question?
So why do you subtract 1 from the cosine k pi?
Because that's the value at 0. Again, I'm taking all of this stuff out, so all we're looking at is the cos kx.
Oh.
Cos k pi
I got it.
is cos k pi.
Yeah, you plugged in.
Cosine of 0
You plugged in.
is 1.
Okay.
Yeah. Okay, so now, yes, go ahead.
If cosine of 0 is 1, and then you're subtracting it, and doing another negative, so what should we
The negative I've factored out. I've factored it completely out of the picture, so all we're evaluating is this cos kx. All right, so now, there are 2 cases. Cos k pi. What happens to cos k pi? What if k is 2?
It's 1.
Cos k pi is 1. Yeah. So I'll trip around the unit circle, and cosine of 2 pi is 1. But what if k is 3?
Negative.
-1? That's what I think. Yeah, okay, so this depends on, what does it depend on? Whether k is,
I got my trig down.
yeah. This depends on even or odd for k. So we'll write it in this way. It is, okay, let's do the k even first of all. If k is even, cos k pi is 1. The whole thing is 0. So we'll get 0. K is even. And if k is odd, what happens here if k is odd? The cosine reduces to -1. So now I get a -1 minus 1 is -2 times -2 is +4. So this is 4 over k pi. Okay, so now we have a rule for all of the coefficients. And we can build this function out of sines and cosines. Let's try to do that. So now our f of x, remember that all the a's are 0. So all the cosine terms are out. All that's left is the sine terms. So let's see here. It's b1 sine 1x. What's B1 according to the recipe we just built? Now let's do it this way. B1 sine x plus B2 sine 2x. B3 sine 3x. And so on. Can you tell me what B1 is according to the recipe we just did? Say again. 4 over pi. That's in 4 over 1 pi. How about B2? B2 is 0. B3. Sine of 3x, and now the pattern is clear. 4 over 5 pi. Sine of 5x, and so on. In other words, we have just found the frequency component associated with a frequency of, what would this be? Frequency of 1 over 2 pi. This is the frequency 3 over 2 pi. This is the frequency 5 over 2 pi, and so on. So now we know the frequency components. Maybe we could go one step further with just, anybody have a calculator handy? Oh, I think maybe I already have it, so let's see. Yeah, this is 1.2732 sine x. The next one is 0.4244 sine of 3x. And this one is 0.2546 sine of 5 pi. And so on. Okay, so now we've got just enough time, I hope, to pull up that Falstaff website. Okay, here's our square wave. So, maybe you can click the number of terms. Oh, do we have sound?
Yeah.
Yes.
Is there a sound checkbox?
I got it now. Should we hear something right now?
I would think so. Now I hear it.
What should I push?
Well,
When I
hopefully
increased the number of terms, the sound came on.
so maybe, okay, because the sound is 0 now, so maybe we can get sound but less volume, can we do that?
Okay, yeah, we can do that.
Oh, look at that, we've got complete control of this. Okay?
Too loud stuff?
No, well, it's up to you.
Okay, we'll try that.
So just increase it one term at a time. So there you see this first sine term. That's the period 2 pi, the frequency 1 over 2 pi sine term. And there it is. And if you just touch this with the mouse,
You can do it with your pen.
oh, no kidding. Something just happened there.
Oh,
Why did that happen?
You guys can't use the mouse and the pen at the same time.
That could be it.
Okay, wait. What should I do?
Let's try.
That's fine.
Let's try clear.
Click.
Okay,
Whew.
I think that's square wave again.
Square wave.
Click the square wave. Okay, let's just increase it one term at a time. So 0, and another sine term. Do you hear the overtones coming on? The higher frequency terms? And do you see how the sine is just starting to get closer and closer to that square wave as we add more and more terms? So now, suppose you've got a recording, and you find out that during your whole recording session, there was a train going by, and it has polluted your recording.
Such as Kevin Short.
Yeah, but now that train maybe corresponds to this term right here because it has a specific frequency. And you can take this, go ahead and turn the sound on, and you can grab any one of these components and just pull it down to 0. And you can filter the sound by changing the amount of that particular frequency that is in there. And this is all digital, so you have a digital representation of the sound, and you can tweak it one coefficient at a time. And you can enhance certain parts of it, you can delete certain parts of it, you can change it in any way that is necessary. That's the way modern signal processing is done.
Is that what like the audio corrector, like the voice correction for singers? Is that what they're doing?
Oh, absolutely.
Like
It's-
Britney Spears?
Yeah, I mean, it's definitely based on this. Obviously, we're just dealing with a constant sort of steady sound here. And it's much, much more complicated if you have sounds that are changing over time. But let's see, I read a little bit more about this yesterday, and I think that the sampling rate, the typical sampling rate for CDs is something like 48,000 samples per second. So all of this is happening 48,000 times a second, and you can take little teeny pieces of the sound and splice it together into one continuous stream. And then, as things need to be changed, like if Britney Spears is having a bad day and she just needs to fix something, you can fix it. Yeah.
So is that how they make electronic music?
Boy, you know, I think, I guess I'm not really sure about this. The whole thing has to do with taking a signal of some kind, like this square wave, sampling it, and then digitizing it from those samples. And so the short answer is, yeah, it's related to this. The long answer is really, it's much, much more complicated. We're just seeing this, we're just scratching the surface of the whole business right now. But I hope you can see how you can take an original function, represent it by its Fourier approximation, and then frequency by frequency, you can change things in that Fourier approximation.
I just put together, as you were talking, like as you went through the end of that every cosine term turned out to be 0, and look down at the bottom, that's where the cosine terms are represented.
Yep.
They're all
There's
0,
cosines.
because
And here are the even
that's what we figured out those
signs.
coefficients would be 0.
And the odd signs
Again,
are,
smaller and smaller.
the whole signal is built out of odd numbered sine terms. And so it's the odd sine terms that matter. And then you have this underlying sound matched by, or enhanced, I should say, by all of these overtones, as they're called. Yeah.
So yesterday we said like music when it's like processed, it's zeros and ones. So when you're finding like the zeros and ones here, is that like how it tells like what to play?
Yes. All of this, we're doing it in just good old base 10 arithmetic, but all of this stuff would be represented in binary form because that's all that an iPod or any kind of a digital music player, that's all it recognizes. So it's all turned into zeros and ones, bits and bytes. Any other questions? Okay, well, you've been a good audience, you've been interested, and that's all I can ever ask for.
Do you have any questions in general for him? Something you thought of overnight that you were wondering?
Are you still teaching calculus next year?
Me personally? No. Not in the fall. In the spring, I don't have the slightest idea what I'm teaching. I'm teaching 2 sections of Calculus 1 and linear algebra. You know what linear algebra is? Yeah. Solving simultaneous equations like x plus y equals 3, x minus y equals 7. That's linear.
I think matrices when I think linear algebra.
Absolutely. Absolutely. That's part of it. And if we took this another day or so, there'd be a matrix involved. There'd be matrix and matrix inverse and solving big systems of linear equations. Your MP3 player cannot do integrals. Let me give you that. So, do you know how they avoid doing integrals? There it is. They do trapezoidal rules instead. And the trapezoidal rule is something that can be done fast, on the fly, instead of actually integrating. So that's another step in the process. All of that stuff that you thought was nobody would ever apply to anything, it's heavily used in the digital signal processing. Enough said. Do you have any other general questions about anything that I might know about?
Thank you so very much for being
Okay.
here.
Says you have 8 days left in your school year? Something like that.
Yeah, we need a more visual representation. There you go. These guys are seniors, so they only have the pink days left because they graduate.
I see. Yeah, but who's counting, right?
Yeah.
Yeah. Well, my school year ended well, actually, the day before yesterday, I turned in my final grades.
That'll be the next thing next year. They'll be done that much earlier.
That earlier, but it's hard work. Going to college is hard work.
All right. See you Monday. Bryce, I have one more thing for you if you're not done. You're not fine.
This is just such a nice website because it allows you to tweak the individual terms, visualize and hear
I
all
think
of
it's so
them.
cool that you did the square and there's the square and here it is. The even terms are down here and the odd, the
Yeah,
even
and
terms are here.
I'm trying to point to one of these. I want you to consider point
That's what you would calculate.
Yeah, that's exactly, that's 4 over 3 pi.
That you actually had on.
Oh, yeah. Yeah, very definitely.
Yeah.
Also, I'm guessing that the wavelength equation and sigma notation, and then that moves up, that works for any wavelength, correct?
Any waveform?
Yeah, but we're for like, say, like a light wave or.
Oh, yes.
photons.
Oh, yeah.
Okay.
Yeah. The Fourier analysis is the bigger the term that's more broadly applied. But the Fourier analysis essentially is useful in any waveform. So that sounds like physics, and I don't do physics.
Yeah, I do physics.
That's all, yeah, that's his favorite.
Actually, I do physics, but I have no expertise. My older brother, however, has a PhD in physics, and his specialty is optics. So,
And my favorite thing in physics is, I really love quantum mechanics.
You can't.
As quantum physics reveal all of this.
oh yeah. Well, and in fact, there might be studies of light that are not quantum physics.
Yeah,
That are, and I really don't know.
yeah, quantum physics.